everyone for sticking around, and thanks to the organizers for having me over. It's nice to see many of you after many years. This is a problem I worked on when I was a postdoc with Dan Gusfield in UC Davis, I think about 93 or so. I started working on it again recently. And the reason I worked on it again is because it involved converting a combinatorial result to an LP rounding result. So that's what I want to tell you about. This is the main message of the talk. I'm going to tell you about minimum Poise trees. And I define Poise of a tree in an undirected graph as the sum of the diameter of the tree and the maximum degree of any node in the tree. Okay, so that's what the Poise of a tree is. Okay. Long time ago, I gave a log n approximation for the Poise of a tree. And I'm going to describe that approximation algorithm for you. And recently, I wanted to find an LP rounding algorithm for the same problem. Okay, and I'm going to show you how I was recently able to do that with my co-authors, who I should mention. My brilliant grad student, Jenny, who just started this week at Waymo, and colleagues at Northeastern, Raj Mohan and Ravi Sundaram. And then in the end, I think I'll definitely have time. This is a really simple talk. I'll tell you how I got to this problem at all, from some problems in rumor spreading. All right, so before we get started, if I gave you a graph, a complete graph, and I asked you to minimize the diameter of a tree, what's the best tree? It's a star, right? Yeah. If I gave you a complete graph and I asked you to minimize the degree of the tree, what's the best tree? It's a path. So what is the solution for the minimum Poise? If I give you a complete graph, I want you to find a tree of minimum Poise. What will it be?
Path of stars.
It's a path of stars? Or? No. Can do better, maybe. Log n over log n, great. So basically it's a tree where the diameter is roughly equal to the degree. So it's actually a complete D-ary tree of depth D. Right? So you sort of balance the diameter and the degree, and you get log n over log n because D to the D is about n. Right? You want to fill the nodes of the tree. Okay, so that's the kind of thing I'm looking for. Okay, all right. Okay, so we got that over. So this is the outline of my talk. I'm going to give you that first log n approximation by taking a detour to some slides I had from 10 years ago, and then I'm going to repurpose the same slides to show you the LP rounding, and I'm going to use even older slides to show you the application of this thing. So that's the three parts to my talk. Okay, so actually, if you don't remember anything from this talk, this is really a nice trick. And this trick will remind you of the Friis-Gagliardi Maffioli solution for ATSP that Lazzi mentioned, and many other things that happen today. So it's a very simple idea for building spanning trees, which have good say, objective functions that are low with respect to two or more criteria. So if you want to find multi-objective spanning trees, this is a really simple idea. So the idea is called, it's based on matching, so I called it matching-based augmentation. It's an iterative construction heuristic, so you start with the empty tree, and you keep adding edges until you get everybody connected. Okay? And the idea is that by looking at a certain simple solution decomposition, you should be able to tell what the subgraph you want to add at each iteration is. So this is going to be an interactive talk, as you can tell. Okay? And I'm going to propose this heuristic, and I'm going to give you the Poise problem again. And I'm going to ask you to tell me what that subproblem is. And by solving the subproblem, we'll be able to add some edges to the graph. And then by adding the edges to the graph, we'll actually reduce the number of connected components we have on our way to forming a spanning tree by half. Okay? And then we'll do this about log times, and then we would have gotten a connected graph. Okay? So here's a simple illustration. I'm going to give you a log n approximation for minimum spanning tree. Okay? So I start with every node I start with the empty graph. Remember, it's a construction heuristic. Okay? And what I do is, while there is more than two clusters, two connected components, I'm going to just find a minimum cost matching between any pair of connected components. Okay, so you get the algorithm. So I start, I have empty graph, I find a minimum cost matching, I use the matching, I get half the connected components. Now I just find a minimum cost matching between them. And of course, it takes only log n base 2 because I'm halving at each time, right? And why is it the case that the cost of the matching that I built is at most the cost of the minimum spanning tree? This is the main question. And for this, you need a really simple observation. Okay? Imagine the optimal solution, which is the minimum spanning tree. And imagine that you have 6 components currently in your algorithm. And I pick one node from each component. Those are the x's here. These are representative nodes and 6 components. Okay? Now, I can find a way to match up these 6 nodes, one node from each component, by using disjoint paths in the spanning tree, like that. Okay?
So you really meant T-join and not matching?
Yeah, never mind all that. I mean, that's all just lingo. But, this is really what I mean, right? I mean, fine, it won't be a T-join, as you'll see in my... Okay, so you see, if you give me a tree and you give me an even number of nodes, it's really easy to pair up those even number of nodes so that the paths between the pairs are edge disjoint. Okay? It's really simple because you take any pairing and suppose a couple of those pairings, suppose I paired this guy with that guy, that still works. Okay, suppose I paired this guy with this guy and that guy with this guy and they overlap, I can just repair them locally. Okay, and that will reduce the number of crossings and you will get to a disjoint pairing. Okay, so it's really simple observation. Okay. All right, so now you see, no matter what set of components I have, if I pick one node from each component, I can always connect them up using a matching whose cost is no more than the cost of these paths. And therefore, the minimum cost matching I find is at most the sum of the costs of these paths, which in turn is at most the cost of the spanning tree. So that thing. Okay. Therefore, at each step, I'm using cost at most the cost of the spanning tree. Okay. So this is
triangle inequality, or?
Well, I don't really need triangle inequality because the place where I cross over from this component to that component, right? I mean, because I don't need it because there'll be an edge where I'll get out of this component and go to some other component, right? And that edge will connect me out somewhere else. So I don't really need triangle inequality for this.
Then you need T-joins.
Okay, Michel is really hung up on T-joins. Okay, this is a T-join of those even number of nodes in a tree, if I have an even number of components. So, and every tree has a T-join whose cost is at most the cost of the tree. That's what he wants me to say. Thank you. All right, okay, good. So now here's what I want to do. I want to use this lemma to figure out what subproblem I should be solving for the problem I want to solve. Okay? So here's the problem I want to solve. Remember, this is my Poise. So this technique, I call it matching-based augmentation for obvious reasons. I also teach a lot of MBA students, so that's why I like that name. Okay. All right. So given a graph, I want to find a tree of minimum poise. One way of defining poise is find me a tree where this is more general than that, where the path length between any pair of nodes in the tree is at most some bound d. And you minimize the maximum degree of the tree. Right? It's the same thing. Instead of summing, I put a bound on 1. Okay? So now suppose I want to apply MBA on this problem. What is the subproblem I need to solve when I want to connect 2 clusters? Okay? So let's imagine an optimal tree. This is a tree where the diameter is at most d. Okay? And the tree has maximum degree whatever the objective function is. Okay? And now I need to find a way to connect up these components, these representatives, using what? I need to find a paths that allow me to connect them up. The paths have to have length at most d, and the degree that they induce at any node should be at most whatever the minimum degree is. So it's basically a path matching using paths of length at most d, where I minimize the node congestion of the paths. You guys with me? So this is how I'm proposing that we use MBA to solve whatever problem you have, if it's possible. Okay, which is you examine the optimal tree, you come somewhere, and you've got all these different components you're trying to connect. And now this tells you what you should do now. You should find a matching between these representatives. The edges of the matching are paths of length at most d, The objective function is to minimize the congestion induced on nodes by these paths that you, okay? That's a flow problem, right? It's just a simple flow problem saying connect this guy to somebody else, right, with 1 unit of flow. Make sure that the flow paths are of length at most d. You can write that down. And the objective function is minimize the node congestion of the flow. You can write that flow problem down. You can randomly round it, right? So I've actually just told you how to solve the MBA, the Poise problem using MBA. Because I just have to solve the subproblem. I need to define an auxiliary graph, where I want to find this matching, where I match everybody to somebody else using paths of length at most d, and I minimize the node congestion, okay? And you can do that, and that's what I did in my first paper, right? And that gives you, so this is what you do. You start with an empty subgraph, right? Every node is a representative, right? And you iterate until you're connected. You set up this L-bounded min-degree matching or min-degree node congestion problem, right? Add it to the solution and then continue until you get a big tree. Okay, you guys awake? Yeah. Actually, I think you're not awake. Yeah. Okay.
Are you solving that in polytime?
Yeah, I can solve the matching problem in polytime. Yeah. Yeah. That's a detail. We can do that later, or yeah. But I think you guys are still not awake. Yeah.
So you're writing an LP for this, or you?
Yeah, I'm going to write an LP for, I have a bunch of nodes, representatives. I need to connect each node to some other node. That's a flow problem. The paths of this flow have to be of length at most L. Sure, I can do that. Okay, yeah.
I guess I'm thinking if you're using randomized routing, don't you use a log?
Fine, okay. I mean, that's a detail I'll get rid of in the end, but yeah, polylog, We're now in polylog land. Okay, I still think you guys have not picked up on something important. Yeah, what's it, Michel?
No, I mean, I'm still not convinced about that one. So about the length L bounded, because, I mean, if you take, for example, if the length is 1,
okay,
then it's, you're looking for matchings.
That's right.
So if you formulate it as a flow, it's not going to work.
So so let's just think about what I want to do. If I want to connect a representative to some other representative, okay, I set up a multi-commodity flow where I connect all the other representatives to a dummy sink. And I want 1 unit of flow going from this guy to the dummy sink, right? And I do that for every possible node. So I get 1 flow per terminal. And I now have to bound the length of this flow. That's all.
The issue is that
what are you guys worried about? Yeah. Sorry?
As you add these things.
Good. Yeah, I think Chandra is awake. Okay. Because diameter is not additive. See, if I add 1 subgraph and it gives me degree d, and I add another subgraph from another iteration, it gives me degree another d, over L iterations or k iterations, the total degree will be k times d. But diameter is not like that, because if I form a path of length L to connect up these representatives, and then form paths of length L to connect up those representatives, and form paths of length L, right? You see, the diameter is not additive, it's actually doubling. So, this is broken. Right? I can't add these paths and hope that the diameter of the final graph. But I fixed this a long time ago, don't worry, okay? You just have to promote one of the representatives up. Okay? And when you do that, it's sort of like you're sort of keeping the center of this path. So instead of the center, just use one end and then pull that end up. So when your k levels up, right, every terminal you started with is at most k times d away from the current center of the graph. Okay? This is another interesting idea. So this is a good idea for low diameter graphs. If you're trying to find low diameter things, right? You connect up things with low diameter paths. You promote exactly one of them to the next level. So in the next level, the set of representatives you need to connect are these 4 guys. Okay? Then you connect them up and then promote one of those guys. Inductively, someone at iteration k, right, will be at k times d. D is the length of one of these paths from the center. All right, so I think that pretty much fixes it. And in the end, what do? You actually found a bunch of these paths. It's a maze of paths. You added them all together, right? And you have one huge connected component. What tree do you output? But remember, in the very end, you have one root, right? Just find a minimum breadth first tree from that node. right? Just find a node of minimum diameter starting from that node, okay? Everybody will be within distance log n times d from there, and diameter is, a degree is additive because we're just adding these conjections, okay? And finally, you've got yourself a low Poise tree. Okay, so that gives us this theorem. Okay, this MBA algorithm gives us a spanning tree where we are within log n of the minimum Poise of what? Well, in all my proofs, I use the optimal tree to show that my flow problem is feasible. Okay, so unfortunately, my approximation guarantee is with respect to an optimal integer solution. Okay, an optimal solution from which I extracted the flows. Okay, so what I really wanted to do recently was to prove the same theorem, but I wanted to prove it with respect to an LP. Okay, you might ask why, and I'll get to that at the end of the talk. Okay, because I needed the LP to do recursion and some algorithm. Okay, so but I'll get there later. I may not get there at all, but that's fine. Yeah. Okay, so but let's just try to figure out what the LP for Poise will be. Okay, but maybe I should pause here and see if you have any other concerns on. Are you okay, Michelle? With the Okay, you all right? Yeah.
Thank you.
All right. Okay. So what's the LP for Poise? Well, it's the first thing you would think of. Okay, I have degree and diameter, so there are two sets of variables. Okay, it's really easy. Okay, it just looks a little complicated, but there's a variable for which edges go in the tree. Okay, and for every terminal, okay, I'm now doing this for Steiner tree. You know, I don't want the spanning tree, but I just want a Steiner tree. Okay, I have a set of paths that I can use of length L. Remember, like I'm doing length-bounded paths, okay? From the tree, from the terminal to some root. Let's say I know a root who needs to be in the tree, okay? One of the terminals, okay? So these are paths of length L from the terminal to the root. I need to pick one of them because in the final tree, right, I want to be able to reach the root from any terminal in a path of length t, at most L, okay? Then what do? Well, I say the length of these paths that I pick. Okay, actually forget about this sub L. It's just a set of all paths. The length of the paths I pick should be no more than some length bound, call it L2. Okay, so this is just the average length, right? Okay, and what is the degree? Well, if I pick a particular terminal, right, all the usage of the paths of that terminal should not exceed the installation of the edge. You know, I can only use a path through an edge if I install the edge. So XC is just the installation variable on the tree. Okay, and the degree of a node is just the sum of the edges incident on a node. So that's just the degree bound. Okay, so the degree is L1. The length of the path from any terminal is L2. I minimize L1 plus L2. Okay, so it's just a natural LP. You might say if L is long, this path system is exponential and all of that, but you know we can fix all of that. Okay, it's not it's some details. Okay. All right, so now what I want to do is to run my same algorithm and the same idea, but I want to replace the performance guarantee with respect to this LP. Okay, so I want a true LP rounding algorithm for Poise. That's what I want. Okay, if you all agree that this is an LP for Poise, you know, I just want an LP rounding algorithm now. Yeah.
You can run the same algorithm and prove it with respect to this. No?
Correct. So I just need to make sure that the flow that I was trying to find is with respect to this LP. Okay? But there's a slight subtlety here, which is I don't really get flows between terminals in this LP. Here all the flow paths are going to the root. Okay? And they are independently, all these flow paths are independently using copies of this X variable. You see, I think some of you are starting to see this, okay? It's just not easy for me to start with this LP, the first LP you would write down, and give me a solution to the multi-commodity flow problem. Remember what the flow problem is. From every terminal, you need to get to some other terminal with a flow of 1. All the paths should be of length about L, whatever your guess is, okay? And the union of these flow paths should have congestion no more than something like L. Okay, how do you get this flow decomposition from this LP?
Twice. Can't you go in and out of the root?
But if all of them go in and out of the root, they're using the edges closer to the root a huge amount of times. You see, if they have k nodes, I have k over 2 guys going up and down, the edges are getting used to the extent k. I only want to use one copy of this tree.
So you need to show that at any point in the algorithm,
Right.
for the matching problem, there is a feasible solution.
That's right. That's right. From this LP. That's exactly what I want. Yeah.
So you show that take the dual and
No, don't need duals and all.
Bottom-up clustering,
Bottom-up clustering, that's the same MBA idea you want to do?
until you have two of the things you want to connect, and then just use that subtree to connect them using the LP solution.
Right, that might work. So he's saying, like, don't let two guys go all the way to the root. Wherever they meet, just shortcut them. Okay, but then we still have the mess of making sure that the overusage of these flow edges. Okay, but it's actually a very clean solution. Okay, that's what I want to tell you about. I just one slide about it. Okay, so I still want to use the same strategy. So this is something you all know now because I want to use the same doubling thing. I just want to bound these flow paths with respect to the LP. This is just what we've been discussing so far. Okay, to do that, I'm going to use a very simple path packing theorem. Okay, this is a good thing to know. Okay, if I gave you an Eulerian graph with some terminals t, okay, call a t path as a path between any two distinct terminals. Okay, it's the type we want, right? For a particular I want to go from I to somebody else. That's a t path. Okay. Now, this is all theorem which shows that if the connectivity from any terminal t to any other terminal, that is, think of this as isolating cut, right? The min cut that isolates t from all the other terminals is at least c of t, right? Sorry, okay? Then you can actually find a packing of these t paths of this cardinality, okay? I want to first convince you that this is actually the maximum you can get. Why? Because every t path, how many t paths can go out of a terminal? At most c of t, because all the t paths have to go to somebody else, and the min cut separating a terminal from all the other terminals is c of t. So I can get c of t paths from every terminal t, but every path has two endpoints, so I have to divide by 2. Okay, so this is the maximum possible number of t paths you can get, right? Because every t maximum I can get out of t is c of t, right? And I have to divide by 2. Okay. Now, how do you show that there exists such a t path packing? This is a beautiful example of Marder and Lovaas's splitting off theorem. In an Eulerian graph, you can always split off the edges incident on a vertex so that all the other pairwise connectivities are good. So split off all the terminal nodes, non-terminal nodes. What you have left are exactly the c of t edges, and then you roll back the algorithm, you get the paths. Okay. So if you didn't follow that, just scratch that. Okay. But this is actually a great, if you're teaching about splitting off, this is actually a nice example for splitting off. Yeah. Great. So now you see how I've got my paths.
You could do the other thing is you can pack Steiner trees,
right?
And then integrally.
But I can't pack Steiner trees. That's the problem, because I only have the solution for one tree. See, my whole solution just supports one Steiner tree. How can I pack more than one?
No, because in the fractional sense, no, because you want to pack an X. I'm a little confused here what CT is, but...
Okay, see, so let me tell you what it is. You take the solution to this Poise LP, the LP we wrote, which minimizes length plus, right? And then what you do is you just scale everything by some big number. That's what you're thinking of, right? So just scale by the largest number in the denominator. Then you get this multi-graph, okay? 1 becomes m. So that means every terminal which used to have one connectivity to the root, remember all the paths had to go to the root, now has m connectivity to the root. Yeah. Okay, so now what's the isolating cut from any terminal to any other terminal? It's m. Okay, so now what should I do? Well, I have to be a bit careful because these t paths may be really long and I want my paths to be short. But we know how to deal with that. Just filter the long ones away. Take away the paths which are longer than, say, 4 times L. Okay, you'll still have 3/4 of the flow left, right? So you keep 3/4 of the flow, okay, and then you've got all these paths which are t paths which start from a terminal and go to some other terminal, okay? They are of length 4L, okay, and then I've got the flow packing I need. I basically have about 3/4 flow from everybody going to some other guy, okay? And somebody was worried about randomized rounding. I think it was you. Oh, Yuval was worried about randomized rounding. You don't need randomized rounding. You can use this old, packet rounding result. It's like column sparsity rounding. So, I have this path packing now. The paths are all of length about 4L, Okay, and the congestion, by the way, the congestion at any node is only doubled, right? Because to make the graph Eulerian, I just had to double everything. Okay, so now I can find an actual dependent rounding of these flow paths where I exceed the node congestion by that 4L.
But here you're using the fact that you have an additive thing.
Yeah, here I really do use the additive thing. Yeah,
It is a fixed bound you want to do.
that's right. That's absolutely right. Yeah. Okay, so this may be a little fast, but are you guys worried about this? Yeah. Okay, all right. You don't seem worried. Okay. So basically, this just says I have a solution which is a fractional flow, which gets everybody from which gets a terminal T out, right, to some other terminal, and all these flows have path lengths at most 4L because of my filtering. I threw away paths which are bigger than 4L. Okay, so now if I look down the set of nodes on which I have the node congestion, right, a path goes through at most 4L of them, so the column density of any one of these paths is at most 4L. And this rounding method says that you can take this LP solution and round it to an integer solution where the additive loss in every one of these constraints is at most this sparsity. So instead of 2LC, I'll have 2LC plus 4LD in the final integer solution. Okay, but LC plus LD is my LP bound. So that's it. So I got my now. If you really want details, what you'll get at the end of this rounding is from everybody you'll get one path to somebody else. Okay, so now you can build this pseudo auxiliary graph where everybody has one edge going out. Okay, you'll get some kind of a bunch of pseudo trees like this. Okay, but now I can't use all of these paths because one of these trees may just be a long path. And if I added all of these paths, I have the risk of blowing up my my diameter by an unbounded amount. But that's if you've been following me so far, you'll probably realize that from these trees I can either take the odd levels or the even levels. Okay, and then just use one of these two path systems, and that will make sure that my diameter is bounded. At this point, I probably lost all of you, but this is about right. Yeah. Okay. Yeah, but basically, the trick that I had for merging pairs works also when I merge these representatives in stars, because stars only increase the diameter by 2 times d rather than just additive d. So it's not that difficult. Okay, so I think I've accomplished what I wanted to do, which is show you at least the main ideas of going from from a combinatorial log k to a LP rounding log k. Okay, so now if you're curious at all, I'm almost done. Why I wanted to do this, I actually wanted to solve this problem where I had a rumor sitting at a node in the graph, okay, and I wanted the rumor to go to everybody else by phone calls. So every day, any person who knows the rumor can call a neighbor in the network and inform that person of the rumor. So in day 2, both of them can get to work and spread the rumor. And in day 3, all 4 of them can get to work and spread the rumor. Okay, so the problem I wanted to solve was, given a graph and a source node under this telephone model where you use a matching from informed to uninformed nodes, what's the minimum number of steps in which I can get the rumor out to everybody? That's the minimum broadcast time problem.
So each one can make one.
Only one phone call. That's the telephone call. Okay. Now, if you trace how a rumor went out in the graph, in other words, if you stepped from a vantage point of a node and asked yourself, how did I hear the rumor? You heard it from somebody, and you direct that edge into you get a directed arborescence. And the objective function that I'm interested in that arborescence, remember, if that tree has depth d, it's taking that many days to do the phone call. If some node has degree d, I have to do these different phone calls on different days. So I get my objective function degree plus diameter, because both of them are lower bounds on my rumor spreading time. Okay? So given a rumor spreading protocol, looking at this tree that tells me how I heard these rumors, I actually get a tree, and the rumor spreading time is lower bounded both by the maximum degree and by the diameter. Okay, so what's a factor of 2? So I added them up, and that's how I got to my Poise problem. Okay, so and then so this was our tree, and then I showed that if you gave me a low Poise tree, I could also broadcast within some factor. This is not relevant. The real reason I wanted the LP rounding is because there's a version of this problem where I don't care about getting the same rumor from the root to everybody. Everybody has their own rumor, and they want to tell their rumor to their mate in some other part of the graph. So this is like the generalized Steiner version of this problem. Right? So it's not the spanning or the Steiner version, it's the generalized Steiner version. I call it multi-commodity, multicast. So it can, when I make a phone call, I can actually exchange as many messages as I want. So there's no bound on the bandwidth of the messages. And I still want to minimize the multicasting time. Now that problem, that's really hard to solve. This multi-commodity multicast. In fact, the best known approximation for this multi-commodity multicast is this, what I call the Mary Poppins guarantee. Super polylogarithmic sub-polynomial, right? Yeah. So super polylogarithmic sub-polynomial, yeah. So it's one of those Mary Poppins problems. Okay. So I really wanted to make this a polylog approximation, and I was able to do that in this paper that I put up in the beginning in the archive version, and we were able to make that a polylog for planar graphs. And to get to that polylog, I needed this LP rounding because I wanted to do a recursion in a planar graph based on this LP. Okay, so that's how I sort of got into that problem. But if you want more details about that, you can read all about it in this archive paper called Plain Gossip. And that's the end of my talk. Yeah. And since we have an open problem session, those are my open problems. These are pretty obvious ones. I think the most interesting one is whether we can actually get an integrality gap of a constant for a spanning tree where I minimize the degree plus diameter, max degree plus diameter. I think it's a pretty natural problem. Maybe one of you guys can do it. That LP, I don't know the gap. So that's, I think, the most interesting structural problem. And I think many of you have many different tricks up your sleeve in this room. So this might be a good one.
Can you take one quick question?
Yeah.
So what would happen with the diameter and the degree you were looking at was weighted?
Right, things get hairy, but you can, if they're all polynomially bounded, you can do the usual, you can weight them appropriately and so on, right? So I think the diameter weights are not a problem.
Right.
The degree weights create a little bit more of an issue, yeah.
Right.
So that's sort of, yeah.
Okay, thank you, Ravi.
Thank you.